Alright, problem number 13 in group theory. Let G be a non-abelian group with 2n elements for an integer n. Part A, if n is odd, show that all elements of G of order 2 are conjugate. Okay, we have elements of order 2 are conjugate, and we have a non-abelian group with 2n elements. So this is definitely screaming Sylow. Okay. So let's see what we have. We want to consider the Sylow 2 subgroups, which are going to have order 2 since there's only one power of 2 in G, because it has order 2n, and n is odd. Okay. Suppose that n is odd, and let G be a group with 2n elements. Consider the Sylow 2 subgroup. Let's consider the Sylow 2 subgroups, which have order 2. Whoops. And we can kind of exhibit one. Let P be a Sylow 2 subgroup. Then P equals the set of, well, it's going to have the identity and it's going to have some other element where X is in G. Okay. And we also know that X is going to have essentially order 2. And so we want to show that all elements of G of order 2 are conjugate. So let G in G be an element of order 2. Then notice that the cyclic subgroup generated by G has order 2 and is a Sylow 2 subgroup. Okay. And we know that Sylow P subgroups are conjugate with Sylow P subgroups. So let G and H in G, in G have order 2. Each have order 2. Then H and the cyclic subgroup generated by H are are conjugate with each other since they are Sylow 2 subgroups. Hence, there exists K in G such that we have that K times, I'll copy and paste it, the cyclic subgroup generated by G times K inverse forgot a space, is equal to the cyclic subgroup generated by H. That should be an L. Hence, I used hence there, so I'll say thus KG K inverse is in the cyclic subgroup generated by H. But we know that G has order 2, and conjugation preserves the order. Therefore, KG K inverse is equal to H. Because H has order 2 as well, so the only elements in the cyclic subgroup generator of H are just the identity and H. It can't be the identity because the identity has order 1, G has order 2, so it has to be H. So every element of G of order 2 are conjugate with each other. So we showed part A. Now we'll do part B. Maybe I should label A and B. So part B says, give an example with n even where not all elements of G of order 2 are conjugate. Okay. Consider S12. Consider S4. Which has order 24, which is equal to 2 times 12, and is also non-abelian. And we want to show that not all elements of order 2 are conjugate. So we're first going to remark that elements of Sn of the same cycle type, or different phrasing, elements of Sn are conjugate if and only if they are of the same cycle type. Remark that elements of Sn are conjugate if and only if they are of the same cycle type. So notice that transpositions in S4 and double transpositions in S4 both have order 2. However, they are not conjugate with each other since they are of different cycle types, one being a transposition, the other being a double transposition. But you can never conjugate a transposition to get a double transposition likewise. Thus we are finished with B.